let's get started with the afternoon session. So this will be a little bit of a shorter session because we have the business meeting afterwards. So we have two talks before the before the coffee break and two afterwards, if I'm not mistaken. Neil Ross will make the start with optimal ancilla-free Clifford+T approximation state rotations.
Yes, thank you. How much time do I have?
So that's a good question. You have
50?
50 minutes.
Okay.
Including questions, so maybe 45.
All right, great. Thanks. Okay, so yes, I will be talking about the problem of finding Clifford+T approximations for Z rotations. And so for those of you who were here on Sunday, this is very related to the stuff Krista Svore was talking about, especially in the second part of her tutorial. Now, the restriction that applies here is that the circuits we consider use no measurements and no ancillas. Okay, so they're strictly deterministic circuits on one qubit. And so I'll be describing a method to solve this problem, but you can sort of think about it as, I mean, it's one algorithm, but it really encapsulates two different algorithms depending on how efficiently you're able to factor integers. So if you know how to factor integers efficiently, right? Say you have a quantum computer at home, then you can use this algorithm. It'll be efficient, it'll run in an efficient time, and it'll produce the shortest possible Clifford+T circuit solving your problem. So given a rotation angle and a precision, it'll find the shortest circuit that approximates that rotation at that precision. Now, if you don't have a factoring oracle, if you're not able to factor integers efficiently, you can still use the algorithm. You just don't try to factor, and it'll still run efficiently, and it'll still produce circuits that are no longer optimal, but very close to optimal. Now, a disclaimer: this second property of the algorithm, that it still runs efficiently and produces short circuits in the absence of a factoring oracle, relies on a number theoretic assumption about the distribution of primes that I'll detail or I'll mention a little bit later. Okay, so just for a little bit of motivation, here are some gate counts. So up until recently, the best known method to find approximations for unitaries was the Solovay-Kitaev algorithm. And it produced circuits of size log 1 over epsilon to the fourth, roughly. So that if you wanted to approximate a given unitary up to precision 10 to the minus 20, say, then right here, you'd need about 60,000 gates. And of course, if you wanted to, say, approximate a unitary to precision 10 to the minus 1,000, for some reason you really want to be extremely precise, then you'd need this many gates, okay? Now, on the other end of the spectrum, in the case of the Clifford+T gate, there is a result giving us an average lower bound on the number of T gates, or essentially on the number of gates required to find approximations, and it's given in this right column here. So you see that for 10 to the minus 20, you only should need about 200 gates. So the purpose of this talk is to essentially bridge this gap. Now, so when you wanted to learn about the Solovay-Kitaev algorithm, you needed to learn about geometry, okay, about Lie groups and commutators. But as of recently, in 2012 essentially, if you want to learn about quantum compiling, then you should learn about number theory. And as far as I know, this is due to a paper by Klushnikov, Maslov, and Mosca, who were the first ones to use number theoretic methods to solve problems in quantum compiling. And since then, many of the recent advances in the field have been using these or related tools to get these optimal or asymptotically optimal decomposition algorithms. Okay. So I'm going to go on a little bit of a detour. And before we talk about approximations, I'm going to tell you about grid problems. And we'll see later how these come in handy for our particular problem. So we're going to be interested in a ring, Z adjoint root 2, okay? So the elements of this, it's the collection of elements of the form A plus B root 2, where both A and B are integers. And this collection forms a ring in the sense that you can do, all the usual ring theoretic operations on these elements. And what's particularly interesting for us is that the ring comes equipped with an automorphism that we call the bullet here, which act a little bit like complex conjugation in the sense that it maps the element A plus B root 2 to the element A minus B root 2. And using this automorphism, the bullet, you can define a norm on your ring, a number theoretic norm, by stating that the norm of an element alpha is alpha bullet times alpha. So this norm for us has two important properties. The first one is that for any alpha, the norm of alpha is an integer, always. And also, the only element of Z root 2 whose norm is 0 himself, okay? Now, this bullet automorphism is an extremely non-continuous function in the sense that if you take two elements of Z root 2 that are really close, then their bullets are going to be really far apart. And the reason for this is it's actually quite easy to see. If you take the product of the distance between alpha and beta and the distance between alpha bullet and beta bullet, okay, right here, then what you get is the absolute value of the norm of alpha minus beta. So if alpha and beta are distinct elements, then this quantity here is going to be an integer greater or equal 1. Okay, so this product is bounded below by 1, so it's impossible for both the members of the product to be small at the same time. Now, this has the following consequence. If you look at, so say you consider an interval on the real line, okay? So in this case, we're considering the interval from -1 to 1, okay? Pictured in green here. Now, consider all the elements of Z root 2 that have their bullet inside that interval. Well, that will define a completely not dense, a discrete and infinite subset of the reals, okay? Because the reason is, well, if their bullet is in B, then the distance between their bullet is bounded above, so the distance between them is bounded below, okay? So we call this set the grid for B. So in this example, you have B is this interval here, and then all the black dots on the line are the various grid elements in the grid of B. So for example, you have -1, 0, and 1 are elements of the grid for B. And then if you move sort of to the right, I think this one is 1 plus root 2, and then 2 plus root 2, and so on. Okay, so this is how you define the grid for B. And as you might expect, if you take a wider interval, you get a slightly denser grid. Okay? Now, here's what we call a one-dimensional grid problem. Say you have two finite intervals on the real line, A and B. The one-dimensional grid problem is to find the elements of Z root 2 that belong to A and whose bullet belongs to B. Okay? So essentially, you're looking for the elements of Z root 2 that lie at the intersection of A and the grid for B. So if you look at this particular one-dimensional grid problem, so you have your interval A here and your interval B here, the black dots represent the grid for B. And so the solutions to the one-dimensional grid problem are these black dots that lie inside this interval A here. So in particular, in this case, there's 4 solutions. So we want to solve these problems. And the nice way to think about Z root 2 to attack grid problems is not to think of it as a dense subset of the line, as it in fact is, but rather to think about it as a discrete subset of the plane. Okay? So here you have Z root 2 represented as this lattice in the plane where, say, for example, this point here is the point with a coordinate 1 and b coordinate root 2. So it's the element 1 plus root 2, okay? And you can think of z root 2 as this lattice. And then you can also think about sort of this diagonal here being the a plus b root 2 line. And then the action of the bullet would be to map these points to the a minus b root 2, which is the anti-diagonal in this case, okay? Now here's why it's interesting to think of z root 2 as this lattice rather than as a dense subset of the plane, because given a one-dimensional grid problem, so you have these two intervals, the solutions to the one-dimensional grid problem are these points of the lattice, these points of the lattice that lie inside this 45-degree rectangle. So, right? So you're using your interval A and your interval B here and drawing these 45-degree lines. They define this rectangle, and the solutions to the grid problem are these lattice points that are inside this rectangle. Now, roughly, the number of solutions to the grid problem is proportional to this, to the area of the rectangle. And moreover, if both the intervals are large enough, okay, so that you get a rectangle that looks a little bit like a square, like a little bit fat, then it's rather easy to enumerate all the solutions to this problem, pardon me. What you do, in essence, is you first, look for the solutions on the x coordinate, on the x-axis, and then looks for the solutions on the y-axis. Now, one thing that's a little trickier is when, instead of having a fat rectangle like this one, you have a very long and very skinny rectangle. Now, in that case, the area of the rectangle is still big, so that there should be many solutions, but you can no longer so straightforwardly look for the solutions along each of these axes. So the trick here is to use scaling. What you do is you consider the element of z root 2 that we call lambda. It's just 1 plus root 2. This turns out to be a unit of the ring, so that it has a multiplicative inverse. And what happens is that instead of considering this hard case of the grid problem for A and B, you're going to consider the slightly easier case of the scaled grid problem, where you consider the intervals lambda A and lambda bullet B. So the geometric effect of this is to transform this long skinny rectangle back to sort of a fatter one, so that then you can solve that problem and map the solutions you found there to solutions to the initial problem using the inverse of lambda. So using this trick, we have a solution for one-dimensional grid problems. So given two intervals A and B, we can efficiently enumerate all the solutions for this grid problem. There might be none, but we can enumerate them all. So the next step is to take this kind of problem from 1 dimension to 2 dimensions. So what we consider here, instead of the ring z root 2, is the ring z omega, where omega here is e to the I pi over 4. And so this is a subset of it contains root 2, but is this time a subset of the complex numbers, and we think of them as the Euclidean plane. And then we sort of want to generalize this notion of grid problem. So the first thing to do is extend the bullet operation from z root 2 to z omega. And then given this, we extend the notion of a problem. So instead of considering intervals, like we did in the one-dimensional case, we're now going to consider convex sets, okay? Bounded convex sets with non-empty interior. But the definition of the grid is essentially the same. You look at this convex set B here, and you consider all the elements of Z omega whose bullet lies inside of B. This, again, forms an infinite and discrete subset of the plane, which is represented here. So for example, in this case, if your set B is this square, you get the following grid. And then if you change the convex set, it changes the geometry of the grid. Okay, so here's the grid for a circle. And if you were to consider an even more arbitrary convex set, like an ellipse, you get the following grid. And the notion of a two-dimensional grid problem is just, this time you're given two convex sets, A and B, and you're looking for the elements of Z omega that lie at the intersection of A and the grid for B. So here you have B is this green circle, and A is this pink ellipse. And so this particular problem has 1, 2, 3, 4, 5, 6, 7 solutions, right? So there's some particular cases, some particular choices of convex sets for which we know how to solve the two-dimensional grid problem. The easiest of those is when both A and B are upright rectangles. Okay, so they're the Cartesian product of two intervals. Or you can think, essentially it's just two rectangles that are lined up with the x and y axis, or whose sides are lined up with the x and y axis. Now in this case, the two-dimensional grid problem reduces to two one-dimensional grid problems. And the reason is just that, glossing over slight details, an element of Z omega can always be written as alpha plus I beta, where alpha and beta are in Z root 2. So what you do is, you first sort of consider the x intervals corresponding to A and B, and that gives you one-dimensional grid problem, which you know how to solve. And then you consider the y intervals corresponding to A and B, which is another one-dimensional problem that you also know how to solve. And then with each of these solutions, you can recreate the solutions to the two-dimensional grid problem. So if both the sets are upright rectangles, then we know how to do it. But of course, convex sets are not necessarily upright rectangles. Now, so the next case in order of hardness is when you have sets that are not necessarily rectangles, but that are still upright. So here, what I mean by for a convex set to be upright is the following thing. Look at this A here, this ellipse. To measure its uprightness, what you do is you draw the smallest upright rectangle that contains it. We call this its bounding box, so it's that red box here. And then the uprightness of A is the ratio of the area of A to the area of its bounding box. So that gives you some number between 0 and 1, and the closer the number is to 1, the more upright your set is. Now, the reason this, basically in the two-dimensional grid problem where both the sets are upright, you can still solve the problem because what you do is you draw the bounding boxes and then you solve the problem for the bounding boxes. And because your set are upright enough, then among all these solutions that you've found, some of them you're going to have to throw out, but not that many. So the proportion of elements of Z omega that you found that are solutions to the actual problem you're concerned with is sufficiently high that you're not wasting too much time. Right? So typically here, you would, when you're solving the two-dimensional grid problem for the rectangle, you'd enumerate that point and that point, which are not actually solutions you're interested in. But the hard problem is when you have sets that are far from upright. So if you look at this ellipse here, then that's the typical example of a set that's very much not upright. It's long and skinny, and it's slanted at this angle. So if you were to enumerate the solutions to the problem for the bounding box, most of the points you find would not actually be solutions to the problem that you're really interested in. So in this case, you'd be wasting a lot of time. So the question is, how can we make sets upright, right? We want to do the same thing that we did in the one-dimensional case, where we used scaling to transform a hard grid problem back to an easy one, and we want to do the same kind of technique here. Now, in the two-dimensional case, we consider an operation that's slightly more complicated than just scaling, namely, we're going to act on the set using well-chosen operators. So the linear transformations we're interested in are those that preserve z omega, okay? The idea is that if these operators map z omega to itself, then they're going to map solutions of one problem to solutions of another problem. And if, moreover, these operators are invertible, then we'll be able to like retrieve solutions for the problem we're interested in. So here's some grid operators. You have, okay, well, R is a rotation. You have A and B are scalings. Okay, there's various transformations of the plane that have the property of preserving z omega. As it turns out, those were all the ones that we were interested in. And the key proposition here is that the action of a grid operator preserves solutions. So if you have the two-dimensional grid problem for A and B, and you apply G to A and G bullet to B, then there's a bijection from solutions to one problem and solutions to the other problem. So maybe it's clearer geometrically. So let's go back to our initial, the two-dimensional grid problem that I presented earlier, this one with 7 solutions. So here, the solutions are these points that lie in A. Now let's look at the action of the grid operator on the grid operator B, which is a shearing, on this particular grid problem. Well, when you apply B, you get this problem. So you'll note that there's still the same number of solutions. And also, the pink set is a little more upright. So that's nice. At the beginning, it was pretty far from upright, and now it's a little bit better. What could be a problem, though, is that we did make the uprightness of A better, but arguably the uprightness of B worse, right? Because at the beginning, B was a circle, which is very much upright, and now we've transformed it into a slightly ellipse that's slanted. So it's not obvious that given a grid problem, we're going to be able to find a sequence of operators so that we can make both the sets upright at the same time, which is what we actually want. So when we got to this point, Peter wrote this little game that we could play to try and test out some operators and get a feel for which ones would be useful in a proof, and maybe convince ourselves that it was possible or that it was absolutely impossible. So here's the game. You have these 2 ellipses. You can't quite see the tips of A here, but it's very much not upright. And you can apply some transformations. So, you can do some rotations and some shearings and shear it back. So you can play around and sort of see if you can make them upright. So Peter got extremely good at the game. I was hopeless. So I brought a little cheat sheet to solve this particular instance. So here's a solution to the problem, okay? I'm not going to be very smart about it. I'm just going to do it. So you do 1 rotation, then a few shearings, then another one, a rotation, and a shearing. So slightly better, arguably, but you could do more. If you now do another shearing, 3 rotations. Oh, did I mess it up? Let me see, B. Yeah, I did mess it up. All right, so let's be satisfied in that case. So I think what I meant is this is great, completely sufficient for our purposes. All right. So okay, what happened is we played around with the game and we convinced ourselves that it was probably possible, and then remained to find a proof that this is actually the case, which eventually we did, although it's a little bit painful, but you can prove that given 2 convex sets A and B with non-empty interior, then there is a grid operator that's going to make them both 1/6 upright, and you can efficiently find this grid operator, okay? it's some crazy case distinction, but you can prove that this is the case. And then from this theorem, you get as a corollary that there is a solution to two-dimensional grid problems. Namely, you'll make the sets up right, and then solve those problems, and then map your solutions back. Okay? So that's it. We know how to solve grid problems, and now we can go back to how to find approximations for rotations using Clifford+T circuits. So, okay, this is the Clifford+T group. It's generated by the Hadamard gate, the phase gate, the scalar omega, and this T gate. So there's the first thing I want to tell you about is some results about the structure of the elements of Clifford+T, okay, of the Clifford+T group. So what does a Clifford+T operator look like? Well, surely you could always write it as a sequence like this one, okay? A Clifford operator, a T gate, a Clifford operator, a T gate, and so on. Every Clifford+T operator could be expressed in this way. But this is not very interesting because it's completely not unique. Okay, given a Clifford+T operator, you could find many such representations for it, so you can't get much information from these representations. What's significantly more interesting is this result from 2008 of Matsumoto and Amano, in which they prove that a Clifford+T operator admits a normal form that you can express like this. So here the normal form is written in the language of regular expressions, but this is how you want to read this. So going from left to right, say, it means start with an optional T, so either a T gate or the empty string, then follow it with an arbitrary, this is the meaning of the little star here, an arbitrary number of syllables, either HT or SHT, and then finish with a Clifford operator. So for example, here's an example of an operator given in its Matsumoto-Amano normal form. So it starts with a T, and then there's about 10 syllables, okay, HT, a couple SHTs, and so on, and then it ends with the Clifford operator, S cubed omega to the 7th. Now, what's really great about this result is that, so first of all, you know, every operator admits a Matsumoto-Amano normal form. And moreover, this normal form is unique. So that if two given operators, you know, if two given Clifford+T operators have the same Matsumoto-Amano normal form, then they're the same operator. And finally, another important property of this normal form is that it is T-optimal. So this means that amongst all the expressions in the generators for the Clifford+T group that represent your operator, the Matsumoto-Amano normal form is one of those that has the least number of T gates. Okay? And this is important for us because the Clifford gates are generally considered cheap and the T gates expensive, so that when we're finding expressions in Clifford+T for given operators, we're really trying to minimize the number of T gates, okay? Really, when I'm talking about length of an operator, I really talk about T count of that operator. So of course, the T count is just the number of T gates that appear in the operator. So for example, this W here has 11, T count 11. Okay. Now, you can, so a nice consequence of this result is that you can use it to derive the information theoretic lower bound for the T count that I mentioned on my second slide, I think, okay? Because you can essentially count the number of distinct Clifford operators that use no more than n T gates, okay? And the number is going to be this, 192 times 3 times 2 to the n minus 2. So that's the number of distinct Clifford+T operators that use at most n T gates. And then you can use this result to get the lower bound by just noticing that, well, you need roughly 1 over epsilon cubed balls of radius epsilon to cover SU2. And to make sure that every operator can be approximated using Clifford and T gates, you need one such operator in each of the balls. So you get the following, inequality, and solving for n, you get your lower bound. I mean, this is an average lower bound, right? So it means that in the typical case, you'll need this many gates. Okay, so that's a first very nice result about the structure of these operators. Another one that's also really important for us is the paper by Kluzhnikov, Maslov, and Mosca. I think this is the same one that I was talking about earlier. So in that paper, they solve the problem of exact synthesis for Clifford+T operators. So that problem is somebody gives you a unitary operator, and you want to decide if it's inside the Clifford+T group, and if the answer to that question is yes, then you also want to produce a circuit for that operator. And so they gave an effective solution for this problem, and their characterization is the following. If you have an operator like this W that's unitary, then it sits inside Clifford+T if and only if its entries are of this form. So this means essentially that you can write your operator as some power of 1 over square root of 2 followed by a matrix with entries in Z omega. Okay? So a unitary operator is in the Clifford+T group if and only if it is of this form. So for example, the operator that I mentioned on the previous slide, or 2 slides ago, given here in its Matsumoto-Amano normal form, has the following matrix. Okay, so it is indeed 1 over square root of 2 to the 7, and then some elements of Z omega. Now, the other great thing about this paper is that they give an algorithm to transform a matrix of this form into a circuit. And then, so I don't think it produces a Matsumoto-Amano normal form, but then you can use their algorithm to rewrite the circuit in its normal form, should it not already be in that way. So they give an efficient algorithm to determine if your operator is in Clifford+T, and to construct the circuit if it is. So it's a really nice sort of algebraic characterization of Clifford+T operators, where you just really only need to look at what the entries are like to determine if it sits in the group. And another very important thing is this power of square root of 2 here. So every integer, k here, such that you can write your matrix as 1 over square root of 2 to the k followed by a matrix in Z omega, we call a denominator exponent of that matrix. And the smallest such k, okay, so this is a non-negative integer, so the smallest such k is the least denominator exponent of the matrix. Now, what they also showed is that the minimal t count, to represent a given operator, is a function of this k. So that you could essentially read the t count off the presentation of the matrix. And so I mentioned, because this is the case that's going to interest us, that in the case where the determinant of W is 1, more or less, for all intents and purposes, the t count of the resulting operator is 2k minus 2. Okay? And so we're going to use these results for our approximate synthesis algorithm. So in the approximate synthesis case, you're given an arbitrary operator in SU2 and a precision, and you're asked to find a Clifford+T operator that approximates U that you were given up to epsilon. And moreover, you're trying to minimize the number of T gates needed for this representation. And the idea is that what we're going to do is, first of all, we focus on Z rotations. So it's a restriction on the problem. We don't consider arbitrary elements of SU2, but only elements of this form here. Okay? Now, given such an operator, we're going to be looking for one in this form, so the form described by KMM. So we find one of those that's close to RZ theta, and once we found it, we can use the KMM algorithm to transform it into a circuit. So really we look for one of the, so the goal becomes find such an operator, epsilon away from RZ theta, and try to minimize K while you're at it, so that you're going to minimize the T count of the approximating circuit. And at this point, the crucial observation is that if an operator of this form, okay, approximates RZ theta, if and only if its top left entry belongs to this region here in blue, which we call the epsilon region. So really, whether or not a matrix of this form approximates RZ theta is a condition that you can that only applies to U, well, the top left entry, so it's really U over square root of 2 to the K. And it does not depend on T whatsoever. So you just, so now the idea is the following. You're given your angle theta and your precision epsilon. You use those to construct this epsilon region. The epsilon region relies both on the angle and the required precision. So you get this region here. And now, well, what you do is you look for a U and Z omega that lies inside of this region. Well, actually, I guess you look for a U and Z omega such that U over square root of K with as small a K as you can lies in that region. And then whenever you find such an element, we call it a candidate, you check whether or not you can make it into a matrix. Okay, so you find the U, and then you try to solve this equation for T. If you can solve the equation, then this matrix, constructed like that, will automatically be unitary. So you first look for the candidate U, and then whenever you have one, you check to see whether you can make a matrix out of it. And as soon as that happens, then you're done. So now let's look at how we solve those two little problems. So the second problem, solving a Diophantine equation, amounts to solving an equation of this form. You're given a psi that belongs to Z root 2, and you look for a T in Z omega such that T dagger T is equal to psi. Okay, psi is just 2 to the K minus U dagger U. So you're essentially trying to split psi into T's. I mentioned that, okay, there's this necessary condition. It'll come in handy in the next slide, but both psi and psi bullet have to be greater than 0. But so what's sort of nice about this and about in number theory, sort of in general, at least for somebody who's not really a number theorist, is that it feels like 200 years ago, Gauss already solved all of our problems. He just did so much stuff. So there's a pretty good theory of when you can do these things. And in fact, there is a probabilistic polynomial time algorithm that decides whether this equation has a solution or not. And if it has a solution, it will provide you with one, provided that you can factor this number n here, which is psi bullet times psi. So if you can factor n, then you just feed this factorization to your algorithm, and it'll determine whether the equation 1 here has a solution or not. So if it has a solution, great, you can construct your matrix. If it doesn't have a solution, hey, that candidate was not viable, let's move on to the next one. Now, so of course there's this, right? We have to be able to factor n for this to work. But, and this is where our number theoretic assumption comes into play. There certainly are numbers that we can factor easily, namely primes. Primes are easy to factor. So the question becomes, we're going to go through candidates. Pick a candidate, construct this psi and then this n, try to factor it. But if it's not prime, you might never succeed. So what you do is you just try just a little bit. Put a cap on how much you're going to try. And if when you reach that time, you haven't been able to factor it, then consider the candidate not viable and move on to the next one. And now the problem becomes, how soon are you going to reach a candidate such that the produced n is actually prime, so that you can factor it and sort of get on with constructing the matrix? Well, we don't really know. But we assume that this happens just as often as it would for any random number of roughly the same size. Okay? So this is our number theoretic assumption. We haven't proved it. I'm certainly not a specialist on the distribution of primes. I don't think I could. It would be fantastic if somebody could, or maybe could reduce it to some other better known number theoretic conjecture rather than this rather specific one. But in practice, it appears to be true. Okay, we've never had any problems running the algorithm, but this, of course, this is not a proof. Okay, but now, assuming that this part of the problem is taken care of, all that's left is finding candidates. Well, this turns out to be just a two-dimensional grid problem, okay? Because what you're looking for, so the necessary condition from the previous slide will hold if and only if for your candidate u bullet over square root of 2 to the k is in the unit disk. So finding candidates is really just finding a u in z omega and a k such that u over square root of 2 to the k is in the epsilon region, here in blue, and u bullet over square root of 2 to the k is in the unit circle. Okay? And this is just a two-dimensional grid problem with a little scaling, okay? But it's a two-dimensional grid problem, so we know how to solve them from the first part of the talk. So here's the algorithm. You're going to enumerate candidates in order of increasing k. Okay, so it's like you're enumerating the elements of the matrix in order of increasing t count. So you start with k equals 0 and you sort of move on, finding all the candidates, and then every time you find one, you try to see if you can complete it into a matrix by first computing psi and n, try to find a prime factorization for n. So if you have a quantum computer, that'll always succeed in no time. If you don't, just try for a little bit, but not too much. And whenever a prime factorization is found, check whether you can solve this equation. If you can, then you return the W. You've succeeded in finding an approximation. If you can't, you just move on to the next candidate. Okay, and I'm almost done. Here are the results. So if you have a factoring oracle, then the algorithm is optimal. It'll output the circuit with the least number of, a circuit with the least number of T gates that solves your given problem instance. And in the absence of a factoring oracle, the algorithm is nearly optimal, so it'll yield circuits of T count m plus log 1 over epsilon, where m, for some technical reason, is the second to optimal T count. So in the typical case, m will be given by the information theoretic lower bound of, k plus 3 log 1 over epsilon, okay? And moreover, you can use the algorithm to get an upper bound and a lower bound for the T count in each problem instance, because what you do is you're enumerating these candidates and trying to construct a matrix every time. Now, there's some candidates for which you can determine that they're not viable. So those don't count. But there's some, in the absence of a factoring oracle, where you weren't able to decide, you weren't able to factor, so you sort of left them to the side, and potentially that's a solution. So that'll give you a lower bound on the T count for that problem. And then of course you get an upper bound by the actual solution that you construct. And the algorithm runs in time polynomial log 1 over epsilon. So here's some numbers, okay? So it's sort of like the first two columns are the ones from the second slide. And then here you have the lower bound and what the algorithm actually found. So this was for, I think, angle pi over 128, okay? So you see it hit the lower bound at 10 to the minus 10, but it was 8 away in the case of precision 10 to the minus 1000. So I'm pretty much done. I just wanted to give you a quick demo. So you can, the algorithm is, you can download it from Peter's website, and you can, find some approximations. So say you want to approximate pi over 147 up to precision 10 to the minus 10. Well, there it is. Here's an approximation, and it's written in Matsumoto-Amano normal form. And if you wanted to approximate it up to precision 10 to the minus 70, it'll be a little bit longer, but here it is. And you can also ask the algorithm to give you some stats. So if you put this S flag up, it'll give you, so here you have, okay, it's just gigantic sequence of Clifford+T gates, which is the circuit that approximates your rotation. And it also gives you the T count of your circuit, 702. The lower bound was 698 for this particular problem instance. So you're 4 away. And it also gives you the matrix in the form prescribed by the KMM algorithm. Okay. And nope. That's it. Thank you.
Thank you very much. We have time for questions. Yeah, John back there.
Will was bringing it. So there's one step, well, several steps, but one that I didn't understand, but one thing I wanted to ask about.
Yeah.
Where you're checking for whether you can write this thing as a matrix.
Right.
At least in the way you described it, you check equality, and it seems like you've assumed real precision math. So there's an extra approximation hiding out in there, which is maybe okay because the whole thing is only trying to get an approximate answer. But do you have like careful bounds on how that works, or is this another thing that just kind of works in practice and you're not worried about so much?
Well, okay. So you're talking about basically when we're solving trying to solve these equations with extremely small numbers, and we encounter round-off errors.
Yeah.
Yeah. So this could happen. We only do the arithmetic up to a certain precision.
Right. But
I don't have any precise idea as to how much what the kind of imprecision we're dealing with. If that was your question?
Yeah.
Yeah. No, I don't know.
But presumably one could work that out too, and somehow.
Yeah, probably. But I haven't done it, and I can't do it right now.
Fair enough.
All right. Anyone else? We have plenty of time. Yes, Minchu.
Could you say anything about non-unitary, non-rotation gate? So because you only
right. So there's certainly here the restriction. So we're only approximating Z rotations. Now, if you're given any special unitary, you can decompose it using Euler angles in 3 Z rotations and 2 Hadamard. And then you could approximate the 3 Z rotations individually. So then you're no longer optimal, but you're still not, it's not so bad, right? But as of right now, we don't have an optimal solution for the arbitrary case. Hopefully soon, but not yet.
Great, yeah. Steve?
I have possibly a naive question that exposes my ignorance of number theory. But
Okay.
this looks sort of like a generalized Pell equation where instead of having a rational integer on the right-hand side, you have something in the ring z adjoin root 2.
Right.
And so what I'm concerned about is like the number of bits that you might need to specify the prime factorization. Like the way the theorem is stated, it says provided that the algorithm is given the prime factorization, right?
Right.
But it seems to me that this is sort of like finding a fundamental unit in a Pell equation, which requires you can't do that in general because even the number of bits is very large.
I see.
But I don't know.
No. So that will just instead of showing your ignorance of number theory, it'll show my ignorance of Pell equations. I really don't know. Sorry, but good question. I'll look into it.
Okay, well, if there are no further urgent clarifications, let's thank Neil once more.
Thank you.